So we're sitting here with Don Fisher, the president of the Railroad Museum of Long Island, and we're going to be talking about some of the things that happen to railroads. This is all part of our ongoing story about trying to learn how to make things safer and more reliable, and we're all familiar with railroads, so this is a good place to start. So you want to mention what we're sitting in first?
Sure. We're pleased this morning to be videotaping in a 1960s caboose, and this is what we call a bay window caboose. It was one of the last series of steel cabooses the Long Island Railroad had built for them in the late 1950s into 1960. And this car was built by the American Car and Foundry Company, and this was used at the end of the freight trains of the Long Island Railroad. For many, many years, the railroad gained much revenue by running freight, not necessarily passenger service, but freight service. And with freight trains, you needed a place for the conductor, for the brakeman, the switchman, to have an office, a place to get in out of the weather. And for safety purposes, the caboose, usually a brightly colored car, was placed at the end of the train so that proceeding trains would see it from a distance and hopefully stop in time and not run into the back end of the freight train. It also was the office where the conductor of the train would keep his waybills, knowing where to place full cars along the route and where he would pick up empty cars to take back to New York City. It was also a place to keep tools and maintenance equipment that was used by the brakeman and by the switchman to maintain the train while it was out and about on a line. Now, freight trains were not a superior train. Freight trains were inferior to the passenger trains. The passengers of the time had to get to where they wanted to go. So the railroads allowed passenger trains the greatest freedom to move as quickly as possible along the main lines from Greenport and Montauk into Penn Station. The lowly freight train did not have priority, and they had to rumble along slowly from siding to siding, getting out of the way of the passing passenger trains and also dropping off these cars of material, fruits, vegetables, everything from tractors and washing machines, prefabricated homes, to feed, seed potatoes, anything that you could imagine. Now, while the train was moving along, the freight train, it was very important for the brakeman and the switchman to sit in the seats that I'm sitting in right now. And they would look out the windows and they would watch the cars. And particularly, they were looking at the turning wheels under the cars. In the day, we had what we called friction bearings. These were in the days before ball bearings or roller bearings that we use today. And they needed a lot of maintenance, these friction bearings. There was webbing that would be in the bottom of the receiver for the axle. That webbing was soaked in oil, and the oil, through capillary action, would come up through the webbing and coat the bottom of the axle as it turned, keeping it cool as it rotated below a friction bearing, what we call brasses, which is a little bit of an incorrect word for the friction bearing, because the surface that actually carried the weight of the axle was covered in babbitt, a combination of lead and tin and other amalgamated metals that was very soft and smooth with lubrication that allowed the axle to turn underneath it. The brass part, where we get the name brasses, was the holder of the babbitt and sat up underneath the bolster in the assembly for the axle. Very important that every morning, each one of these axles, friction bearings, was checked for proper oil. If there was not enough oil to come up through the webbing, through the waste material to the lower part of that axle, friction would build up. No oil, no protection between the steel axle and the babbitt. Heat would be produced, and we could have a failure. In the worst case scenario, the axle would get so hot that it would actually break. So as our train is going down the road, we hope that the car knockers, the men and women who worked in the rail yards, had checked all of our axles in the morning. But we could never be sure. So the brakemen and the switchmen would sit in these chairs and look out these windows and watch the wheels of the preceding cars up to the locomotive. If at any time along the route those axles and assemblies started to smoke, we'd know immediately that we had a hot journal box. There was not enough oil, it was not getting up to the axle, it was not coating that axle in the babbitt, and we were getting real superior friction and heat. And probably if we saw smoke, we knew that the webbing and the waste was on fire. Behind me is a lever that goes to the emergency brakes. The brakemen and the switchmen sitting here watching the cars ahead would send out the alarm, throw the brakes into emergency. The engineer would know that there had been a problem. The train would stop. And then it was the job of the brakeman and the switchman, the conductor, the engineer, the fireman, to come back and meet at the affected car and see if they could repair it. They had tools here on the caboose to do the repairs on the road. They had oil. They had additional webbing, the waste that would go in there, and they'd do the best that they could to get the train down the road. Now, if the damage to the axle was too great, then they would limp to the next siding, and they would put the car off on that siding, disconnect it from the rest of the train, leave it there. And the shop forces would have to come out from, in our case, Richmond Hill, the Hillside Yards, Morris Park, Dutton Train Electric Service Area, and they'd have to go out and fix the car out in the field. Some of the things that they might have to do is whoever was getting the material in the car might have to come and unload it and lighten the car there on the spot on a strange siding. The shop forces would come out, repair the car, and then it would be picked up and taken back into the city. Today we don't have those issues because ball bearings, roller bearings were developed, and all of our train axles now run on much cooler, much efficient roller bearings, to the point where we have laid off men and women from the work of switchmen, brakemen, and in some cases conductors on freight trains across the country. They no longer need these people because the technology and the equipment on our trains today is so great, it's so safe, that we've been able to reduce the number of workers, reduce the amount of benefits paid, reduce the amount of wages paid to people that need jobs. Now today we use interesting technology called FREDS, the flashing rear end device, end of train device, and I have a rather simplistic one here that I'll show you. This has replaced the caboose. This has replaced the men and women at the end of the train that used to watch for the hot boxes in the old journals. Along with this, flashing at the end of the train to protect that train from oncoming additional trains behind it. Some of these have sophisticated electronics and radios in them. This one's very simple, but the ones that are used across the country have a transmitter and receivers and sensors here, so that if the train should lose air in its brake system at anywhere throughout the train, this rear end device senses it and sends an emergency signal up to the engineer who would stop the train. So we have this as a remote sensor and transmitter at the back of the train, senses any change in the brake lines, and tells the engineer to stop his train safely. Additionally, along the side of our railroads across the country, we have sensors that actually count the number of axles that go by, the number of wheels in the train. And once the train passes, a radio transmitter sends a voice message to the engineer giving him or her the count of axles. Now, of course, when they left the yard, they were told by the yard facilities people how many cars they had and how many axles should be coming up on the detectors along the side of the tracks. If for some reason a detector gives a smaller number of axles than what the engineer knows he should have, he immediately knows he's lost some cars somewhere. He'll stop the train and he needs to seriously go back and find the cars. Other sensors along the side of the railway right-of-way, the track, will read temperatures. There are temperature sensors. And if one of the modern roller-bearing trucks is getting too hot for some reason, that temperature sensor will send a radio signal to the engineer, giving him the number of the wheel set and the fact that he has a hot box. He'll stop, and he and whoever he has on his train have to go back and check that out. Also, we have detectors on the side of the road that would notice any shift in equipment or merchandise that might be on flat cars, hanging pipes or hanging hoses, anything that might be amiss. If there is something in an area on that car where there should be nothing, the sensor sees it and again will send a signal up to the engineer saying that he's lost some of his material or he has loose pieces of the car floating about. So today, with the technology of the rear end device, flashing a red light for oncoming trains to know that he's got a train ahead of them, the sophisticated rear end devices giving a reading to how much air is in the air pipes for the brake system, and the side detectors at the side of the road giving warnings for the number of wheels on the train, the temperature of the axles and their roller bearings, and also any hanging material, loose material coming from the car. We've used a lot of technology today that we depend on: radio, computers, sensors, to advise the engineer, one person who may be on that train, that he has a problem and he has to stop. This has all replaced the caboose and the 3 or 4 men and women who used to ride back here for the safety of the freight train.
Great. That's really interesting. So to get to this point of having all these technologies for safety, obviously we learned from things that went wrong before. So I'd like to, talk about a little bit of the history of some of the failures. And sometimes the failures aren't just a technological failure. They have to do with organizations, maintenance. They're human factors. And I think in a lot of the cases with railroad accidents, we see that. So maybe you could take us through any of the ones you would like to talk about. I know there are some in the 1950s we're going to discuss, if you want to talk about those first.
Well, actually, in line with what you're saying and our discussion on the caboose, let's stick with some generalities first.
Okay.
Because it's an interesting evolution in railroading.
Ah.
In the beginning, when you had an engine and a few cars, everything about the procedures, everything about the operation of that train was pretty much manual. The only thing that was running was either the steam engine that created the propulsion or in the future a little gas or diesel engine that moved it. but primarily we were working with steam or horses before steam. All of these cars had to be manually controlled. The technology was the human body. And each car would have a set of brakes. And remember our friction bearings? So the rolling axles and the wheels were rubbing on our friction bearing of Babbitt and brass. And virtually every 3 cars had a man at that time assigned to them. And he was the brakeman. And his job was to run across the roof of each of the 3 cars. As the train started to go downhill, or say they wanted to stop as they came into the station, that individual's job was to run across the 3 cars and turn the manual friction brake to slow the train down. Today, we use air brakes that are controlled from our air reservoir and large compressors located in the engine. And we run air to mechanical brakes with springs and pressure rods or rams that push the brakes in and out on each car. That took us away from a very unsafe, dangerous job of running back and forth across the top of these cars while the train is in service. Now you can imagine you're running around on top of your 3 cars in all kinds of weather, during the day, during the night. It was slippery up there in the winter if it was raining. If it was foggy, you didn't see where you were going between your 3 cars. And you were running an area of about 100 feet. Each car was a little over 30 feet long. You'd have to hop from one car to the other because there was a space between cars where the couplers came together. It was a very dangerous job. Men were constantly falling off their cars, being killed, getting their legs broken, getting their arms broken. It was a very dangerous job to be a brakeman. And you were running back and forth in all kinds of weather. Well, now with the Westinghouse brake system, you could get those guys inside or lay them off, give them other jobs that were safer. And each car was individually braked by its braking system from the locomotive. By turning a valve, the engineer could pass his air down across as many cars and apply the brakes. So right there was a safety innovation with going with air brakes. That design, it got men out of a very unsafe environment of running back and forth across these 3 cars. But that was the only way that we had to slow the cars down and stop them as you came into the engine. So the air brakes was a great safety development to protect lives and get these men in out of a very, very dangerous environment. Probably the two biggest changes outside of propulsion going to diesels from steam.
Right.
And again, all of these things that we're talking about today, and you'll hear me come back to this, affects the number of people working in the industry.
Right. Yeah, sure.
And all of this technology going from steam to diesels, cut out shop forces, maintenance people, people who built many, many steam locomotives, because these parts wore out very rapidly, had to be changed, and it was a big workforce. Going from manual brakes to air brakes. We reduced the number of people working on a train from maybe 10 or 12 down to 4 or 5. So you were losing jobs. And then again, with the safety appliances, friendly rear end device, the trackside sensors were cut out the caboose, and we cut out the brakemen and the switchmen that did their safety watching the train. So every one of these safety changes and developments in rail has also led to the reduction in the number of people working.
Right. What about, I mean, something that I guess happened later on, I'm reading about, is this the sensors, that's part of the automatic speed control system I've read about?
Well, the sensors we've talked about so far this morning are strictly observatory sensors that are watching and observing the train for issues. As we get into positive train control, PTC, centralized train control, which is what we've been working with, The systems that we'll talk about that were developed after the Rockville Center and the Kew Gardens accidents, all of these things actually control the train. PTC, CTC, and their sensing goes through the rails rather than side of the road sensors looking at the train.
Right.
And they're system-wide. PTC, CTC, speed control is system-wide over all of the tracks. The sensors we've talked about so far are very limited to a very specific spot along the route, and they're self-contained. In other words, the sensor is there, it reads the train information and gives the data to the engineer within an area of 1.5 miles. Now, that said, some of these sensors are sophisticated enough that it can upload that data by satellite, by radio wave, microwave, into the company's master data computer system. There may or may not be someone sitting in an office somewhere monitoring all of these trackside devices. But primarily, these trackside devices that we've talked about so far are relative to within 1.5 miles. When we go to the greater train control systems that we've talked about that have been going on since the late 1940s, this is system-wide. And those signals to collect data and affect a change in the train's movement is actually run through the rails. Today, over great distances, we do use fiber optics, we use digital, computers, radio, and microwave to pass information back and forth to the controlling computers. But the actual controlling signal that stops the train, that receives where the train is and what it's doing, is going through the rails. That technology was developed in the late 1940s primarily to eliminate or reduce one train running into the back of the other. So that if a train was in what we call a block, a given area of a rail system, so many miles, we would call that a block. If a train went into that block, the signaling system through the rails senses it, and in the earliest days would talk to the block behind it or the block ahead of it, so that a following train, if it got too close, would be closed down and stopped. With speed control in the earliest days after late 1940s, post-World War II, a certain section of track, we would call a block, would have sensing through the rails of a train coming into that area. That sensing of the train coming in would allow signals going to the block ahead and the block behind, setting up red lights, yellow lights, to let the following train know that before he could go into the next block, he had to wait for that train to clear. We wanted to keep the trains separated, and by having the sensing systems built into the rails, we could do this now. Also, if a train was going too fast, getting too close to the train ahead of it, the system would sense this proximity and it would stop the following train so that it would not run into the back of the train ahead of it. Everything goes back to those earliest speed control devices from the 1940s, and we've built on that using modern technology, the use of GPS. We can look at trains and their movement from satellites all across the country, and by using the data that's collected through the satellites, by using data collected through the rails, yes, and if it's set up to pick up data from the trackside sensors, we can know down to within a few feet where each train is on a track. And if they start to get too close together, if the train ahead slows down, we can automatically, through signals sent to the train and the onboard computers, slow or stop the following train. Ultimately, we should be able to, when positive train control, as we know it today, is set up throughout the entire country, we should be able to eliminate rear-end collisions with commuter and freight trains, because we can keep the trains apart, and as soon as one stops in a block or an area, the following train can be slowed or stopped automatically. Today, the engineer reads this information. The engineers have to push a button, keep their foot on a dead man switch that makes a continuous signal, and it's read by the sensors through the rails. If for any reason the engineer does not touch that sensor switch every 10, 15, 20 seconds, if for some reason his foot comes off the dead man switch, the sensing system realizes there's something wrong with the human controller of the train. We can stop the train.
So it sounds like there should never be an accident ever again.
There shouldn't be, but we do have some accidents, which leads us into talking about some of the accidents that we've had on the Long Island Railroad that are well known. And probably the one that so many people know about is the 1926 wreck of the Shelter Island Express, which was an express train that left Penn Station and went through Jamaica and hot-footed it all the way to the East End, to the terminal at Greenport. And this was a train that brought people of import to their homes on Shelter Island, thus the name the Shelter Island Express. And it was a Friday afternoon in August 13th, Friday the 13th, 1926, that this train was highballing down the main line eastbound to Greenport. And it had two locomotives. One was a Camelback, where the operator or the engineer was actually astride the boiler, and the fireman was at the rear and put the coal into the flaming part, which the firebox, which created the steam. The other was a conventional locomotive. And these two engines were double heading, as we call it, pulling this train at great speed to the East End. Now, the investigation following the accident determined that some part of the switch mechanism, that mechanism that was manually thrown by a switchman or a worker to move a set of rails from the main line to a siding and back to the main line, had fallen out or was loose and had not been properly installed after the work had been done to the switch. There was also rumor, discussion, some thought that sabotage had occurred, that possibly a farmer or someone ne'er-do-well in the area of the accident had purposely loosened these parts. We'll never know if it was the fault of a lax group of workers who failed to put the switch back together after they'd been working on it, or if in fact some sabotage had occurred with the switch. But on that fateful evening of Friday the 13th, August 1926, the train was rumbling along through Calverton on the main line. And as it came up upon the Pickle Works, and I believe the name of the pickle factory was Golden's Pickle Factory.
That's right.
Family by the name of Golden's. And it was a big business here on the East End. Farmers would grow cucumbers specifically for our pickles, our dill pickles. And this was a big business. So we had a large factory there where farmers would bring their pickles and sell them to the Golden family. And they had upstairs great tubs of salt brine that could be directed down into a variety of vats. And depending upon whether the pickles were half sours, where they were only kept in the brine for a day, or if they were going to be kept in longer and made into dill pickles, and the type of spices that were mixed into these various vats, the salt from above could be shuttled down through little conveyors and chutes to make the proper mixture in the vat for the pickles to be cured. So we had a rather large building. It was probably close to 100 feet long, 30 or 40 feet wide. And imagine, if you will, up on the second floor, these supply bins of salt and spices for the mixtures, and down below on the first floor, these vats that had the water and the proper mixes with the pickles in it. That was at grade level, or where the train tracks were. And this being a rather large factory, if you would, or industrial facility for making pickles, it had its own industrial siding where trains could come in and be parked, and the workers would fill the cars with the finished pickle product, and they were sent into New York City to feed people in New York. As our lumbering, fast-moving Shelter Island Express was heading eastbound, it came upon the switch to the industrial siding into this building that I've described. The first engine passed through the switch safely. The loose parts had not fallen out until that first locomotive had gone over. As the second locomotive came onto the switch, those parts fell out, and the switch slid over from the vibration of the trains, the lack of the parts, and it was the second locomotive that swung onto the siding. And as it did, it pulled the back of the first locomotive toward the building. And if you would imagine, the two locomotives V'd so that the first locomotive backed into the building, the second locomotive went forward into the building, crashing into all the vats, wiping out the first floor of the factory. The first car behind the second locomotive followed it into the building and telescoped itself well into the first floor. Now, this movement of these heavy trains and cars wiped out all the underpinnings of the second floor. Also, the damage to the rail car was such that it ripped open the envelope around the car, exposing the inside of the rail car. Sadly, a senator by the name of Fish was in the car, and he was inundated and buried under the salt that came down from the storage bins on the second floor. The story of the time was that some workers had run in and were trying fruitlessly to keep the salt away from Senator Fish's mouth and nose so that he could keep breathing until he was rescued. Sadly, due to his injuries and the force of the salt pressing on him, he expired. He died in this flow, this mountain of salt that came down from the second floor. Some of the other folks on the train was a socialite, a young woman with her two children and their nanny. The two children were killed almost instantly. The nanny who survived had to have her leg amputated in the wreck by doctors from the Riverhead Hospital at the time. They came and they had to cut her leg off to get her out of the wreckage. The mother was pinned and was never told that her children expired, and she died shortly after they got her out, or just before they got her out. Again, one of the stories of the time was that while the rescuers were working to extricate the mother, she actually was fed dinner. She was given a sandwich and something to drink while the workers were trying to get her out. Sadly, she did not survive the wreck. The nanny, the caretaker did, but she lost her leg in the accident. The two operators of the Camelback, one was a John Montgomery from Greenport, and he was the fireman on that train, on that engine. He lost his life, as did the engineer. The operators of the first train, I'm not sure, we'd have to fact check that, but one of those gentlemen may have survived with serious injuries, and one of those gentlemen may have passed away. We're very familiar with Mr. Montgomery living in Greenport. We have some of his personal effects, his oil cans and other things that were donated to the museum through the Sterling Historical Society at Greenport and his family. And those artifacts in the story of the pickle factory wreck are on display at our Greenport site. Truly a tragic situation, something that could not have been expected, but in this case, not so much a mechanical failure, but a human failure or error or sabotage, purposefully, human intervention in the system and the mechanism, losing its parts, so that it failed as these great lumbering locomotives went over it.
Mm-hmm. Okay, it kind of shows the complexity of the system even back then. That all the parts that had to work together, you know, it's even hard to predict what the loss of one small part might cause, because you have so many parts interacting in a system, which again goes to why it's so important to have good maintenance and checklists and always, you know, making sure that things operate, but things happen.
It's always good to have more than one person viewing and checking over life-critical parts.
Yes.
And when you're working with a system of parts, creating more parts of a system, it's very important that each nut and bolt, each nail, each screw has been checked and double-checked before the work party leaves a given area. Mm-hmm. And you know, you look at these big locomotives and you look at the size and the breadth and the weight of rail tracks and the ties and everything about them. Here's a case where these massive pieces all came together to make up a system that was dependent on a cotter pin or a nut and a bolt. And for the lack of that cotter pin or that nut and bolt falling out of two of these large pieces, we lost 7 or 8 people, the destruction of a well-known and operating business. It was a horrible, horrible accident. And we tried to eliminate, or we certainly tried to marginalize that error by having more than one person check things. To that end, when we were using telegraph, when we were using written flimsies, we call them, but actually written notes that gave permission for an engineer and a conductor to take a train forward into the next block area that we talked about. There was always more than one person reading that flimsy and repeating it back to the person that gave it to him. And again, this was an opportunity to check, double check, and triple check, so that everyone understood that yes, it was safe, or no, it was not safe to move your train into the next section of track. This was before the days of positive train control, the days before we had speed control. Everything was done in what we call the dark. It was dark territory. And when you came to a junction or you came to a station, you would receive written permission to move into the next area. And the person giving it to the tower operator, they would each read it and read it back to one another, so that it was well understood before that piece of paper was handed up to the conductor and handed up to the engineer. And again, we've got 2 people on the train that are getting it. So we have 3 people. We have the tower operator who has received it and read it back to the person that gave it to him from up yonder, and now he's taking it and reading it and giving it to the engineer and the conductor, who then are conferring and reading it and making sure that everybody, we've got 3 people that say, yes, you can go into the next section of track, or no, you can't. So the more people that check on our systems, the more people that are looking into the pieces and make sure they're all together, the better, and the less chance of having an accident.
So later on, a few decades later on, there were another actually series of several accidents that occurred in a fairly short time frame with the Long Island Railroad that indicated that there was obviously a need for other safety measures and new technologies. Maybe we can talk about those. They were actually I believe the largest accidents in terms of number of deaths and injuries. So I think it's important that we take a look at those.
We can, because it's interesting how in one case the efforts to create a safe environment, in this case for vehicle drivers and people riding as passengers in automobiles, to make that environment safe, the work to do that created the opportunity for the first in what became a series of 3 accidents, but this one in particular derived from the work to make a safer environment around the railroad for drivers of gasoline-powered and diesel-powered surface vehicles. And I think also we have to look at the economics of railroading at the time, 1950. It was post-World War II. We had a growing airline passenger industry across the United States. Airlines were becoming king. Trains were passé. They were old technology to the people. And if you wanted to move from one city to the other, it was the thing to do, if you could afford it, certainly, was to take the airplane. So nationwide, all of the railroads were losing revenue because they were losing riders to the airplane. This tightened the belts of all the railroads. And in particular to our story in Long Island, it really tightened the belts of the Pennsylvania Railroad, what was considered the standard railroad of the world. In 1960, the Pennsylvania Railroad bought into the individual company, Long Island Railroad, historically to gain access to Manhattan Island and to be able to build Pennsylvania Station, which also opened up the East River Tunnel so that the Long Island Railroad could come into Manhattan with commuters. This was all done as a political ploy to step over a requirement that the New York State Legislature and the city councils of New York had developed, i.e. you could not come onto Manhattan Island with a railroad unless the railroad was owned in New York. You owned a railroad in New York. It was not going to be a Pennsylvania or a Baltimore railroad that came in. And this created a monopoly for the New York Central, which had Grand Central Terminal. The Pennsylvania quietly bought up stock and took over control and essentially owned the Long Island Railroad. All of a sudden, overnight, they had the rights to build Penn Station and come on to Manhattan Island. And as history has shown, all of these railroads through the early 1900s, right up through World War II, prospered. They were our only means of moving masses of merchandise, commodities, and people from one part of our country to the other. And they made a lot of money. And while they made money, there was a lot of pride, and they took care of their railroads. After World War II, with the introduction of the airline industry, the railroads were really falling on hard times. Not only through passengers, but they were losing a lot of freight to truckers. We now had the interstate road system that had been put in, the Eisenhower Interstate Road System, which was basically, believe it or not, a military consideration, so that we could move our armed forces around our country if we were attacked efficiently and rapidly. This is why the interstate system was built with federal money and run from one shore to the other. It opened up the industry of long-haul truckers. That took freight away from the railroads. The airlines took passengers away. So by the time we got to the 1950s, early 1950s, all of our railroads were on hard times, and they weren't spending the money that they used to. Equipment was getting shabby, it was getting older, and the safety systems were not always there. Labor concerns, of course they didn't have the money to pay for enough people to work. The people that were working weren't always getting the type of wages that they wanted. Morale was always on the downfall. All of these economic issues contribute to our accidents, and in particular these accidents in 1950. I like to say that this was kind of the death knell of the Pennsylvania Railroad. It was the beginning of the end of their control of the Long Island Railroad. It was the birth, the planting of the seed that a Metropolitan Transportation Authority, a state agency, should be created to oversee and manage and go to the taxpayers and be able to be a taxing agent to maintain the railroads, to grow and maintain the cars, and all of the safety features that we need to be efficient and run our trains safely. So to get to the 1950 accident in February, specifically, it was a case where the railroad was trying to eliminate grade crossings, where it kept the trains moving slowly so that it allowed cars to go across the tracks, and too often cars and trucks would come in contact with the trains and there'd be horrific accidents. The populations of Nassau County, Queens, Brooklyn was burgeoning. More people, more automobiles, more trucks, and the trains were having more and more trouble getting through, as well as was the traffic going on the north and south roads across the main line. So a series of grade crossing elimination projects had been undertaken, where we either lowered the road so it went under the tracks, or we lowered the tracks so that the road could go in an overpass over the trains. In particular, this was the Kew Gardens, Richmond Hill grade crossing elimination project. And as they were building a new railroad track to go over the road, you couldn't stop running your regular commuter service. So the trains were run on a secondary track around the work site. Now, it was not unusual to create what we called a gauntlet track, so that at sometimes during the day, while the workers were running machinery to do the construction of the overpass, we could decide to move the train another 8 to 10 feet away from the workers by putting it onto the gauntlet. And it was an inexpensive way of creating more space. We laid down 3 tracks rather than 4 tracks. So in the normal circumstances, the 2 tracks on the north side of this assembly would be the main line. But when we needed to move the train farther away from the work area, we would switch it over to the center track and another track on the south. These are individual rails. So imagine 3 rails with a little switching arrangement on each end of the work area. Somehow that fateful day, the gauntlet was left so that one train was moving on the gauntlet while another train was allowed to come in on the main line. Why these 2 trains were going into the same area is of question, and I don't have an answer. But ultimately, these trains sideswiped each other, and essentially peeled the sides of the rail cars like tuna fish cans, peeling them back. And the people who opposed each other, or these two cars, as they came together side by side, were injured and killed. We lost 35 people that day. Horrific accident in a construction area, running around on a gauntlet track. Again, this is human error, my opinion. Why these trains were allowed to go into an area at the same time, I don't know, but it was allowed. I imagine, as I have not read the National Transportation Safety Board paperwork, this was an area that had to be controlled as dark territory. There, because of the construction, there were no positive train control or central train control circuits in these gauntlet tracks. They should have been well observed. They should have been well controlled. But for whatever reason, human error, these tracks were misaligned, and these two trains were allowed to come together and if you will, peel back like tuna cans. This was a real shock because the Pennsylvania Railroad, the mother company, and the Long Island had gone for many, many years without a fatality, had gone many, many decades without having any serious accidents. And all of a sudden, here we had this accident in a construction area. Later that year in August, another train moved into a block area that had been occupied by a freight train. So we had a passenger train coming along at a high rate of speed into a block with a freight train that, because of its utilitarianism, moves slowly from one siding to another. And without seeing the caboose, without recognizing the danger, the following train, the passenger train, ran into the freight at Huntington. And this was in August of 1950, just some 6 or 7 months after the February accident. And in that collision, 50 passengers were killed.
They were injured, I think, in that one.
Yeah, I guess there were injuries, and
I'm not sure about that.
I'm not sure. We may have to fact check whether anybody was killed, but there were definitely at least 50 passengers were injured in that rear-end collision. So again, we had an accident in the same year with serious injuries of a railroad that had been accident-free for many years. And again, you look to the human element. How did a passenger train get into the same block as a slow-moving freight train? Again, the controls that we've talked about, 3 people reading the flimsies, the reports, allowing the train to move into an occupied area. Somewhere, somehow, the flow of information was lost, and we had these trains come together. And the real death knell for the Pennsylvania Railroad, the beginning of the end, occurred on Thanksgiving Eve in 1950. And this was another case where a rear-end collision, this time of 2 passenger trains, in the Rockville Center Station area. One train was slow to move out of the station. Another train came in. They rear-ended, and the cars telescoped into each other. And in that incident, over 80 people lost their lives. And of course, the horror of Thanksgiving Eve, day before a time when families got together, this was a horrific accident that was really very emotional to the families and the entire communities and the people around Long Island to see so many lost at a time of year when you come together and you celebrate the holidays. These accidents, all within the course of less than 12 months, sent great shockwaves through the railroad industry, through the political halls in Long Island and in Albany. And as I said earlier, it was the beginning of the end for the Pennsylvania Railroad ownership of the Long Island, and the seeds had been sown from these accidents to establish the Metropolitan Transportation Authority to oversee and take over the trains. Now, As we review accidents, we always try to find ways to eliminate or certainly reduce the possibility of the accident happening again. One of the items that came out of these accidents was the installation of brilliant red lights at the end of every passenger train on the Long Island Railroad. Now, these were like beacons that were procured by the railroad and attached to the last car on every train. And just imagine a red searchlight. And the theory to this appliance was that a following train engineer would see this red beacon like a lighthouse from a great distance, wake up and realize that there's a train ahead and hopefully stop his train safely. The use of more technology in the speed control area was ramped up and extended into more areas of the railroad, so that if a train had slowed ahead, it would actually be able to stop the following train so that they wouldn't get too close to each other. These advancements have helped to make the Long Island Railroad truly one of the safest commuter railroads in the country. And these changes in technology, the appliances of the red lights to the rear of the passenger trains, all aided in correcting the problems of the 1950s, where so much life was lost and the injuries of these accidents.